Download this code from codegive.com, link in the description below. OK, let's dive into a detailed explanation of the paper 1804.04777, Optimizing Bloom Filter Challenges, along with code examples to illustrate the core concepts. 1. Introduction to Bloom filters. A Bloom filter is a probabilistic data structure used to test whether an element is a member of a set. It can tell you that an element is either definitely not in the set or possibly in the set. It has excellent space efficiency, trading off perfect accuracy for reduced memory usage. This makes it ideal for scenarios where minimizing memory footprint is crucial, even if it introduces a small chance of false positives. Key characteristics. Space efficient. Uses far less memory than storing the entire set explicitly. False positives. Can incorrectly report that an element is in the set when it isn't. False negatives are impossible. Simple implementation. Relatively easy to implement and use. Fast lookups. Membership testing is extremely fast. No deletions. Standard Bloom filters don't support element deletion. Counting Bloom filters can, at a cost. How Bloom filters work. 1. Initialization. A Bloom filter is essentially a bit array of m bits, initially set to all zeros. 2. Hash functions. K independent hash functions are chosen. Each hash function maps an input element to one of the m-bit positions. 3. Insertion. To insert an element, the element is hashed by each of the k hash functions. Each hash value is used as an index into the bit array, and the bit at that index is set to 1. 4. Lookup. To check if an element is in the set, the element is hashed by each of the k hash functions again. The bit at each resulting index in the bit array is checked. If all k bits are 1, the filter reports that the element is possibly in the set. If any of the k bits are 0, the filter reports that the element is definitely not in the set. 2. The problem, Bloom filter challenges and adversarial input. The 1804.04777 paper focuses on the vulnerability of Bloom filters to adversarial attacks. Here's the core idea. Adversarial input. An attacker can craft input that exploits the properties of the hash functions to deliberately increase the false positive rate of the Bloom filter. The attacker's goal is to make the Bloom filter report present for a large number of items that are not in the set. Hash collisions. The fundamental weakness lies in hash collisions. If multiple elements hash to the same bit positions, the Bloom filter quickly becomes saturated with ones. Challenge scenarios. In certain applications, like caching or networking, Bloom filters are used to protect against malicious requests or to identify unwanted content. If an attacker can manipulate the input to trigger false positives, they can bypass these protections or cause denial of service conditions. Example. Imagine a Bloom filter used to identify malicious URLs. An attacker could craft URLs specifically designed to hash to the same bit positions as legitimate URLs, causing the Bloom filter to misclassify the malicious URLs as benign. 3. Paper 1804.04777, Optimizing Bloom Filter Challenges. This paper proposes techniques to mitigate the impact of adversarial input on Bloom filters. It analyzes the problem mathematically and introduces strategies to improve the filter's resilience against these attacks. Here's a summary of the key contributions. Analysis of false positive probability under attack. The paper models the false positive probability of a Bloom filter when subjected to adversarial input. This analysis helps to understand how the choice of hash functions and the number of hash functions affect the filter's susceptibility to attacks. Asterisk countermeasures. Asterisk the paper suggests several countermeasures, including asterisk optimal number of hash functions. Asterisk determine the optimal number of hash functions, k, to minimize the false positive rate, even under attack. The optimal k is not necessarily the same as in a non-adversarial setting. Asterisk choosing robust hash functions. Asterisk using cryptographic hash functions like SHA-256 or Blake2 instead of simpler, faster, but less secure, hash functions. While cryptographic hash functions are slower, they provide significantly better resistance to collision attacks. Asterisk seeded hash functions. Asterisk adding a secret key, seed, to the hash functions. This makes it much more difficult for an attacker to predict the hash output and craft adversarial input, as they do not know the secret key. Asterisk filter resetting, refresh periodically resetting or rebuilding the Bloom filter. This can help to remove the effects of adversarial insertions. The rate of refreshing needs to be carefully balanced with the overhead of rebuilding the filter. Asterisk using different Bloom filter variants. Asterisk considering Bloom filter variants like cuckoo filters or quotient filters that have better resistance to certain types of attacks. 4. Code example, Python seeded hash functions and Bloom filter implementation. Let's demonstrate the implementation of a Bloom filter with seeded hash functions to improve its security. We'll use the hashlib module in Python for cryptographic hashing. This example will show insertion and lookup operations. Explanation of the code asterisk. 1 seeded Bloom filter class asterisk. Asterisk underscore underscore init underscore underscore, self, capacity, error underscore rate equals 0.01, constructor. Asterisk capacity, the expected number of elements the filter will store. Asterisk error underscore rate, the desired false positive rate. A lower error rate requires a larger bit array. Asterisk calculates size, the length of the bit array, and number underscore hashes, the number of hash functions, based on the capacity and error rate. The formulas used are derived from the mathematical analysis of Bloom filters. Asterisk initializes the bit underscore array to all zeros. Asterisk generates a list of random hash underscore seeds. Each hash function will use a different seed. Asterisk underscore hash underscore function, self, item, seed. Asterisk takes an item and a seed as input. Asterisk combines the item, converted to bytes, with the seed, converted to bytes. Asterisk uses hashlib.sha256 to generate a cryptographic hash of the combined item and seed. SHA256 is a strong hash function. Asterisk converts the hexadecimal representation of the hash to an integer. Asterisk applies the modulo operator, %self.size, to map the hash value to an index within the bit underscore array. Asterisk insert, self, item. Asterisk hashes the item using each of the number underscore hashes hash functions, each with a different seed. Asterisk sets the bit at the calculated index in the bit underscore array to 1. Asterisk contains, self, item. Asterisk hashes the item using each of the number underscore hashes hash functions. Asterisk checks if the bit at each calculated index in the bit underscore array is 1. Asterisk if any of the bits are 0, the item is definitely not in the set, returns false. Asterisk if all of the bits are 1, the item is possibly in the set, returns true. 2 example usage, if underscore underscore name underscore underscore equals underscore underscore main underscore underscore colon. Asterisk creates a seeded Bloom filter with a capacity of 1000 and an error rate of 0.01. Asterisk inserts a few sample items into the filter. Asterisk checks if items are present, including one that was not inserted to demonstrate a potential false positive. Asterisk performs a series of tests to estimate the actual false positive rate of the filter. Key improvements and considerations asterisk. Asterisk seeded hash functions asterisk. The most important security enhancement is the use of seeded hash functions. The _hash_ function combines the input item with a secret seed before hashing. An attacker who doesn't know the seeds will have a much harder time crafting adversarial input that causes targeted collisions. Asterisk cryptographic hash functions asterisk using SHA-256, or other cryptographic hash functions like Blake2, SHA-3, provides much better collision resistance than simpler hash functions like hash, or murmur hash. While slower, the added security is often worth the performance trade-off in adversarial settings. Asterisk optimal number of hash functions asterisk. The code calculates the number of hash functions based on the capacity and error rate. The optimal K value should be calculated by considering adversarial setting as well. Asterisk error rate asterisk. The error rate is a configurable parameter. A lower error rate requires a larger bit array, increasing memory usage. You need to choose an error rate that is appropriate for your application's requirements. Asterisk capacity asterisk. Choosing an appropriate capacity is also essential. If you underestimate the number of elements that will be inserted, the false positive rate will increase. Asterisk Bloom filter variance asterisk. Asterisk counting Bloom filters asterisk support deletion by using counters instead of single bits in the bit array. When an element is inserted, the counters at the corresponding indices are incremented. When an element is deleted, the counters are decremented. Asterisk cuckoo filters asterisk offer better space efficiency and support deletion, but are more complex to implement. Asterisk quotient filters asterisk. Another alternative that can provide better performance and space efficiency in certain scenarios. 5. Further optimizations and considerations. Asterisk parameter tuning asterisk. Carefully tune the capacity, error_rate, and potentially the hash function implementation to optimize performance and security for your specific use case. Empirical testing is important to measure the actual false positive rate and performance under realistic workloads. Asterisk hardware acceleration asterisk. For performance critical applications, consider using hardware acceleration for the hash functions. Some CPUs have instructions that can accelerate cryptographic hashing. Asterisk dynamic resizing asterisk. If the number of elements you need to store in the Bloom filter is not known in advance, you can implement a dynamic resizing mechanism. When the filter becomes too full, you can create a new, larger Bloom filter and reinsert the elements from the old filter into the new filter. Asterisk regular refreshing asterisk. As mentioned in the paper, periodically resetting or rebuilding the Bloom filter can help mitigate the impact of adversarial insertions. Asterisk monitoring asterisk. Monitor the false positive rate of your Bloom filter. If the false positive rate starts to increase significantly, it may be an indication that an attacker is trying to manipulate the filter, or that you need to reevaluate your filter parameters, capacity, error rate, etc. Asterisk combining with other defenses asterisk. In many cases, a Bloom filter should be used in conjunction with other security measures. For example, you could use a Bloom filter to quickly filter out known bad requests, and then use a more computationally expensive security mechanism to inspect the remaining requests. Asterisk thread safety asterisk. If you're using a Bloom filter in a multi-threaded environment, make sure that your implementation is thread safe. You may need to use locks or other synchronization mechanisms to protect the bit array from concurrent access. In summary asterisk. The 1804.04777 paper highlights the vulnerability of Bloom filters to adversarial input. By using seeded hash functions with strong cryptographic hashes, carefully choosing the number of hash functions and filter parameters, and considering other countermeasures like filter resetting, you can significantly improve the resilience of your Bloom filter against these attacks. Remember to choose parameters depending on the context of deployment and the adversary you want to defend against. Finally, you need to choose the balance between the speed and the security of your implementation depending on the available resources.